lecture number 7. In this lecture, we're going to be talking about the general purpose input-output pins on the Arduino. And there is a lot going on with these. They're very versatile. And so there's a lot to look at, a lot to consider. What we have looked at to this point is just barely the surface. How to just basically use the general purpose input-output pins. Now we're going to actually go down deeper and see a lot more detail about these things. So hold on to your horses, and on we go. So the GPIO pins have true read, modify, write ability. So that's what makes them general purpose. They can read, modify, or write those pins. So the direction of one port pin can be changed independently of the other pins. So that is the basics of what we've been doing. We've been using them that way. So as we go through here, we're going to be talking about ports and pins. So in the Arduino, there are 3 ports, ports B, C, and D. We talked about that last time. And each of those ports has pins associated with them, pins 0 through 7. So throughout here, when we see, in general, we're going to be talking about port X with pin N. So we're going to have these variables that will be used to identify the various ports and pins. So, for example, here we have port X pin N, and this is what the circuit looks like that's connecting that. So there's some diodes, there's a capacitor, and then there's a pull-up resistor that is also connected. Okay, so that's important to understand. And so this idea of a particular port number and bit number or pin number, we're going to see quite a bit throughout here. So this is the circuit diagram that appears for each pin. Okay, so those other diodes and things are not. That's actually external. Those are things that you could connect up. Here, this is actually the stuff that is connected internally in there. As you can see, there's a lot of stuff going on here. PUD. So there's WX, WDX, RDX, WRX, WPX, and so forth. All of these signals, and these are what those things refer to. Okay, so pull-up disable, sleep control, I/O clock. So the I/O clock you can see coming in here. There's a write to DDRX, a read to DDRX, and so forth. So this is what the circuitry looks like internally, and all these guys are connected to the data bus. Okay, so there's a lot of stuff going on here. And these general purpose input-output pins is a very rich topic. So this is something you may want to come back to and refer. Well, when we get later into the depth of things, looking at it from the assembly language direction, we're going to see there's the detail that's here is very important to know and understand. So I'm going to try to cover it fairly deeply. So let's look into these things. So as I mentioned, there's 3 ports B, C, and D, and this in the 328P pinout. That's where they appear in the chip, but in terms of the actual ports, this is another schematic that shows those things, the different port numbers. So ports D, B, C, and D. Okay, so notice that port C only actually uses 7 of the pins. It doesn't use all 8 pins. So as was mentioned, associated with each port, we have some registers. So these are the 3 main registers that we will be using in working with these GPIO pins. Okay, so it's important to understand what these three things are. Okay, so we need to kind of get those things in mind and be prepared to use them because they're very important. So let's dive in. There's actually a fourth register that is used somewhat, and we'll talk about that at the very end. That's a more general register that appears for the microcontroller, and we'll get to that in a little bit, well, at the end of this lecture. But these three registers, so these are registers inside the Arduino, and actually I say three registers. For each port there are three registers. So since there are three registers, and obviously there are 9 registers altogether, and we'll look at the actual pin layouts in just a bit. But for now, we have port X, we have DDRX, and pin X. So the X here refers to ports B, C, or D. So port B, port C, port D, DDRB, DDRC, DDRD, pin B, pin C, pin D. Okay, so this actually refers to all of those. So port, the port actually relates to the value of the pins on that port. Okay, so that's how you you can either read or write the values of those pins using the port command. Okay, so that's how we can write to those ports. For DDR, the DDR is the data direction register. Data direction. So is it input or is it output? That is determined by what you put into the DDR register. So this is what controls the directions of the pin, whether it's an input pin or an output pin, the DDR register. So the port actually determines the value of the pin, the DDR determines the direction of the pin, and the pin register actually is something that allows you just to read the values of the pins. So you could actually use port to do the reading, or you can use pin to do the reading. The pin only allows you to read, it doesn't allow you to write or to control. So, okay, so now we're going to start getting into some of the depth here. So here are the port pin configurations and various things that we can do. So notice that we have the DDR XN, so port X pin N. Okay, so now we're looking at this at a pin by pin basis, and so basically this applies to any of the pins. Okay, so again we can have each pin either in an input state, an output state, or some alternate function. Okay, and so that's important. Okay, so in terms of input or output, we can have them either in the input states or the output states. Okay, and so how that's determined clearly is by the DDR. Okay, so the data direction register, the pin associated with that port then determines whether it's input or output. So if it's 0, you're getting inputs. If it's 1, you're getting outputs. Okay. However, what actually is on those port values? Remember, port is where you control things. Okay. So that's what controls what's going on with the port, either writing the values or altering certain aspects of the state. Okay, so port, so when I have the system or the pin set up to be as an input, okay, that's 0, and if I write a 0 to that pin, I will be put into what's called the tri-state or high impedance condition. Okay, so that's the true input position. Okay, where when you do a pin mode for a particular pin, and you set it as input, you are basically putting it into this condition here. Okay, you're basically putting it into that condition there. So when you put it into this condition, okay, so it doesn't matter what the PUD pull up pin is doing. When I have 0 there and I write a 0 to the port, I will be in this condition. Okay, and in this case, the pull-up resistor will not be there. Okay, so we have that situation. The next state that we can look at is when it's set up to be an input and we write a 1 to that pin. Okay, so it's set up to be an input, but we're actually writing something to it that's not 0, it's a 1. And in doing so, we have these two possibilities, and it depends on what the PUD is. And in the event that I have 0 here, it doesn't matter what PUD is. In the event that I have 1 here, it does matter what PUD is. And so I have these two different situations. In this case, I have the input with the pull-up resistor attached. So if I have the pin set up as an input and I write a 1 to that pin, that will basically set up my input with a pull-up resistor. So that's how we can access the pull-up resistor in the pull-up resistor in this input pin. Okay, we set the data direction to be 0, that is as an input, and then we set the port pin to be 1, and the PUD to be 0, and that gives us the pull-up resistor. Okay, so that's how we can set the pull-up resistor, okay, on an input pin. So that would be similar to the pin mode where you say input pull-up. Okay, when you say input pull-up, that's actually setting it into this. So this is the state that goes into when we use the pin mode input. This is the state we go into when we do input pull-up. So now you have this other option that can occur, which is a different high impedance state. Okay, and so this is a possibility. Okay, so but these are the two that are most commonly used. Then we have, with the input, we can have two different things happening. I'm sorry, when we set this to be 1, they're output pins, and depending on what we do, what's happening here? Well, in this case, there's no pull-up resistor applied. This is an output, so that means it's a low impedance output, and it doesn't matter what the PUD is, the pull-up direction, so when you have it set to be output, the pull-up is disabled, is basically what's happening. And so basically, when you set the port to be 0, you get output low. When you set the port to be 1, you get output high. Okay, so that makes a lot of sense. Okay, so basically, when you set the port to be 1, then the port value will be determined by whatever you write to it in that write to that bit. Okay, so that is what happens there. Okay, so now it turns out that if you want to go from one state to another, there are some restrictions. In particular, if I want to go from 0, 0 to 0, 1, in order to change from 0 to 1 in the DDR bit, that requires like a write to that port or to that register. And I can't write to that register simultaneously with writing to this register, so I can't actually change both of these values at the same time. So I actually can't go from this state to this state in one command, and neither can I go from this state to this state in one command. So in order to do that, it may be important to think about the sequence of switching. Basically, I'm switching from an input port to an output port. And basically, you need to go through some kind of a transition when you do that. So for example, going from here to here, I may want to first change this bit and then change this bit, or I may, so we need to figure out something to do, and that would work. The other thing that could work is I can go directly from here to here, from this state to this state, and just let the output be 0, and then change this state. So those are some things to consider. Anyway, we basically just can't switch directly between these, and that may or may not ever affect you. And if in fact, if you need to, you may want to put in a delay or something. But these are just some things that can come back to get you and surprise you if you're not aware that they exist. Okay, so let's look at all the registers themselves and the bits associated with those registers. We'll start off with port B. So here are the port B registers. And so when we say port B now, that is the physical port that's associated with that. It's not to be confused with the register named port B. Okay, so the register named port B is a part of port B, but it's not the only thing associated with port B. There's also the DDR from B, and then there's the pin of B. So remember, the port register basically allows us to read and write. So R and W stands for read and write. So in this register, we have all of this information. So as you can see, there are lots of tables like this, lots of information. There's a lot of detail. It's important to be able to have access to this information when you're doing the programming, because it helps you to know what you can do, what these things are, and so forth. So basically, all 8 of these bits I can read and write to. Okay, so this is pin port B, pin 0, port B, pin 1, port B, pin 2, all the way down to port B, pin 7. The default value, so when you start up the Arduino, it's defaulting so that all of these values will be 0. And similarly here, they'll all be 0. Okay. This port this register has an address, 0x25. So in hex, it's 25. And actually, this value depends somewhat. We'll come back when we look at assembly language. There are different variations on this port number, but this port number will work. Okay, this is a number for it. Also associated with this, and in what I have here in this table, is the color actually makes a difference. See how these names are colored? They're not there just for decoration, although it adds a little contrast to the slide. The color here actually refers to the fact that in the Arduino IDE, these names are actually predefined. Okay, and how would I know that? Actually, I just tried it, and it just turned out that yes, they are predefined, and it actually works. But I could not find anywhere in the literature or on any web page that said that these things were predefined. So this is a bonus that you're getting directly from me regarding this information, because it's not readily available information. So, but this name is defined. So I can say port B equals to something and actually assign it something, and that would be comparable to writing that information to port B. Okay, and so also each of these pin numbers is defined in the Arduino IDE. Okay, so that again, that's another bonus that you're getting directly from me, that these numbers these names are actually defined. I don't have to do an include to include a header file that has these names. When the compiler goes, there's already a header file that's been defined that it accesses, and I don't have to actually refer to it directly. Okay, so that's important. Now, on the other hand, these guys, for some reason, are not defined. So even though this name is predefined, these names are not defined. So that's kind of a kooky little thing. But anyway, that's what we have. So it's important to keep it in mind. So the DDR, that's the data direction. Is it an input? Is it an output? Okay, so I can set any individual pin as to whether it's going to be an input and output. So I can both read these values or I can write them. So if I write them and I go back later and it's like, okay, now what did I set it to be? Is this now an input or is it an output? I don't know. I can go read it and find out. And so so notice that when I can't just read a specific pin number. I actually have to go through and I actually have to go through and read the entire register and then extract the particular bit that I want. Okay. Whereas this pin, so this pin actually reads what's on the bit. Okay. And so this is actually the register that's read whenever you input values. Okay. You can use this, but actually this is better to use because remember, pins can change, and so it turns out this is what's called the latched version of what's coming in on the pin, whereas this is not latched. These guys up here. Okay, so this is whenever you read from a pin, this is what you actually want to use, and so if you want to read what's happening on pin B0, for example, so pin that's port B. 0, pin 0. So we showed you last time how ports B, C, and D line up in terms of the Arduino pins, right? The digital pins and the analog pins. So remember that pin B2 actually relates to some Arduino pin. Okay, and so if I want to read digital pin, whatever. I would find the associated port number and pin number to match that, and we'll come back and do a little programming example after a while just to show you how that works. Okay, so these are the port B registers. Each of these registers has a number. Okay, and so I can later on when I come to working with these things, I can actually define these numbers if I need to work with them. Okay, so every register on the Arduino has an address, and so that's actually what this is that's the register address for that register. Okay, so what's important in all of this is that let's suppose that I have set all of these guys to be an output. Okay, so again, that means I have set them all to be 1. Right? Okay, I've set all of these pins to be 1. That means they're all output. I can now, by assigning some value to port B, I can assign every one of those pins a value. That corresponds to writing 7 digital outputs simultaneously. Okay. If you were to try to do this in the Arduino IDE, you'd have to take it pin by pin, and basically that would take you 7 commands. And so, as you can see, being able to work with the ports directly is much more efficient, or speed-wise, than having to do it with the Arduino IDE. So we can already see by going to the registers, we can streamline our code much more. Okay, we can simultaneously write to 7 pins at a time. We can simultaneously, if these are all set up to be input pins, we can do a simultaneous read of 7 pins. Okay, we can read all 7 pins at once. Okay, so again, much more efficient. Or I can read individual pins very easily. I can just say, if pin B7 is equal to 1, or, if it's equal to 1, then blah, 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 do something. So notice that these pins are both read or write. I can read to them or I can write to them. Okay, so that's important. I can read or write to these pins. So we'll see some of that coming out here in our example. These pins, are actually read-only. I can try to write to them, but it won't do anything. If I try to write to them, actually, I don't know if it'll even give an error, but it won't do anything. Okay, so these are read-only, and they're not predefined as to what their initial values will be. Okay, it's not predefined. So you really only want to read these once you've defined, for example, whether it's an input or an output port. Okay, port C has the same kind of situation as port B. So again, all of these names are predefined, so forth. These are undefined, but these are defined. These are defined. Okay, these are the register numbers and so forth. Everything is pretty much the same. But notice that there isn't a pin. Pin 7 on these is not really functional. There's no connection to it. Okay, so if you were to read this whole port at once, you'll get 0 as that 7th bit. Okay, so it's not really giving you any information. That's what you will read when you read that in. Okay, so, but otherwise, port C as a port functions very similar to port B. Similarly with port D, again, just the names are changed to protect the innocent, but no one's innocent here. They're all guilty. They all do the same thing. Okay, so understanding what a particular port does basically helps you to understand what all the ports do. Okay, so that's an important thing. Okay, so and all of this information is available, and so it's helpful to have access to this information because you can use this when you actually are doing programming. So if we want to write to a pin on a port, okay, first we would prepare the pin to be an output pin. Okay, so now if we go back to these ports, notice data direction. The default is 0, which means it's by default defined to be an input pin. So if we don't do anything to the pin, by default it's going to be 0. Okay, so by default, so when your Arduino starts up, your pins are already defined so to be 0, 0. So we saw that if we had 0, 0, it's defined to be an input pin, 0 in a high Z state. Okay, so we are when the system starts up, we automatically know what state it is in. So we don't actually have to, if we're going to use these as input pins, we don't have to do anything. We can just leave them as is, and they will be input pins. Okay, so that's important. So again, that just saves you some code. Since you know that's the case, you don't have to do anything if you're going to use it as an input pin, and you can just leave it alone. Okay, so you really only have to do something if it's an output pin. Okay, so prepare the pin to be an output pin. Again, you'd use the DDR, okay, whatever port you're using, and bit whatever bit you're using. So this is not the name that you would use, but that's the bit you would use, or the pin you would use, and then you would write to that. So you would first set the DDR bit, then you would set the port bit. Okay, again, 0 is input, 1 is output. So it's helpful to remember that. I always forget. I always have to look back because I can't ever remember that 0, that 1. It's almost like opposite, right? 0 and I look like opposite. 1 and O look like opposites. I guess that would be a good mnemonic, right? 0 is input, 0 is I, 1 is O. So it's like if I have a 0, it's not like O, and if I have a 1, it's not like I. So anyway, that would be one way of remembering. I hope I do remember that. Okay. So this is what we do. Now we're going to look at a programming example. How would we actually use this to do a program, to do some programming that we want? Okay, so here's the program. Here's the problem that we're going to work with. Okay, here's the problem. So in the setup function, we want to set up these things. Okay, first we want to set the first 3 digital pulse width modulation pins as outputs. Okay, we want to set those up. We're not going to use pulse width modulation, but we want to set those pins up as output pins. We want to set the RX pin as an input pin, so that makes sense. That would be a receive. We want to set the transmit pin as an output pin. Then the remainder of those first 8 Arduino pins as input pins. So we're going to be using the first 8 Arduino pins, and we want to set them up this way. Okay, so the remainder are input pins. These are output pins, and that's an output pin. So that's what we want to have in the setup part of the program. In the loop part of the program, we want to be reading those pins that we've set up to be input pins and set the corresponding output pins as the not of the inputs. Okay, so what do we mean by corresponding output pins? So RX and TX are corresponding pins, right? One is the receive, one is the transmit. Okay, and then we basically will choose the input pin that is closest to the pulse width to the output pin, and so we'll look at that. Okay, so to get a sense of where these pins are, again, we're going to look at this diagram. Okay, so these are our first 8 Arduino pins are right in here. Okay, and so notice there's an RX and the TX pins. Okay, and so we're going to work with those. Okay, and so notice that's port D, pin 0. So notice these are all port D. So fortunately, we can do this exercise using only port D. We don't have to use port B. We don't have to use port C in this exercise. We can just work with one single port. Okay, so that's handy. It's not accidental, but it is handy. Okay, so these are 2 of the pins we want to use. The others are the pulse width modulation pins. So we wanted to set those up as output pins. So those are pins 3, 5, and 6. And so pins 2, 4, and 7 would be the input pin, the other input pins. Okay, so this is an input. We're going to set this as an input pin. We're going to set pin 2 as an input pin, pin 4 as an input pin, and then pin 7 as an input pin. And then we're going to set pins 1, 3, 5, and 6 as output pins. Okay, so just to kind of recap that, all first 8 digital pins are in port D. The pulse width modulation pins are pins 3, 5, and 6. The RX and TX pins are 0 and 1. And so again, we're going to assign things this way. So the input pin is going to be assigned to pin, or the output pin is going to be assigned to pin 0. Output pin 3 is assigned to pin 2. Output pin 5 is assigned to pin 4. And so these are just the closest pins to those. The output pin is chosen to be the one that's closest to the corresponding input pin. So that's what we mean by their corresponding pins. And so this is how we make that correspondence. Okay, so we're given a problem and we're marching on through. So we've identified what pins go where, which pins need to be inputs, which pins need to be output. And so basically, if pin 0 has a 0 on it, then we're going to have set pin 1 to be 1. If pin 0 has a 1 on it, then we're going to put pin 1 to be 0, and so forth. So these pins are going to be the not of these pins. Okay, so that's what we need. That's what we need to do. Okay, so in our program example, we'll first look at the setup program. Okay, and so we can set DDRD equal to, and we're going to set these bits. Okay, so we're basically what this is doing is setting port D pins 1, 3, 5, and 6 as outputs. Okay, so we're setting them to, so remember 0 is input, 1 is output. Okay, and I can do this, port D or equals all 1s. So that basically, I can do this, and basically what that does is that sets, well, I have this question. What does that do? First of all, what does the or equal do? What does the or equal do? Well, if I have or equals something, so this port or equals that. Okay. So the or equals basically takes whatever's in this register, ORs it bit by bit with this, and then puts the result back in that register. Okay, so that's what the OR equal does. So in this case, that's what the OR equal does. So the next question is, what does this command do? Well, what this command does is it takes this number, takes these bits, and ORs them bit by bit with whatever's in port D. Well, because these are all ones, if I OR a 1 with anything, it's going to give me a 1. So basically that sets all the bits in port D to be 1. Okay. Now we could actually have been more efficient and just said port D equals this is equal to this, and that would have basically set all those bits to be 1 anyway. Okay. So now a question arises, what happens if a bit is written to that has been set as an input bit? So I have an input bit, and yet I'm writing something to it. I'm writing a 1 to it. What does that do? Well, if you go back and recall what we just talked about with the various pins and the different things, we saw that if we set the DDR to as input pins, so wherever it's a 0, if we set the port D, if we write to port D a 1 to that pin, like we're doing here with pin 0, then that basically connects the pull-up resistor. Okay, that connects the pull-up resistor. All right, so and the rest of these pins, so wherever we have an output pin set to 1, that's actually just setting that output pin to 1. Okay, whereas in this case, it's kind of like setting it to 1 in the sense that if there's nothing connected to that pin will go to a pull-up resistor, which means it'll go to 1. Okay, but basically it's connecting in the pull-up resistor. So that's what happens if a bit is written that has been set as an input bit. Okay, so basically here we're setting some of these pins to be pull-up pins. We didn't have to do this. We didn't have to do this. We weren't asked to do this, but that's what would happen if we did this. Okay, it would basically, all the input pins would have pull-up resistors with them. Okay, well that's the setup program, and actually I threw in more than was needed, which can be very dangerous, very dangerous. All right. So is it necessary to set it this way? No, we weren't asked to, and we weren't told we needed input pull-up resistors. So this line of code is superfluous. In industry, it's very common that they don't want you to put in any extra code at all, because any extra code, first of all, could be buggy. Second of all, it requires some documentation. Third of all, it may or may not be associated with the requirements for that project, and if you throw it in, it may actually change how the requirements are met. And so it's in general, in industry, they don't want any extra code at all. So you have to be very careful when so even though this may be a useful thing, it may actually be a problem. And so in general, it's good to not throw in extra stuff like that. Okay, so this command itself would basically set the data direction for all the pins. So it would set pins 1, 3, 5, and 6 as outputs. The others it would leave as inputs. Okay, so in our loop program, we have this. This is the code that we could use to solve that problem. Okay, so pin D0. If pin D0, so notice that pins 0 and 1 are tied together. So what's all this going on here? Okay, so if pin D0 is equal to 0, okay, then what's going on here? These are all very similar to one another. Okay, let's take a look at this one first. If pin D2, so that's input pin 2. If that's 0, then we're going to OR port D with this number. If it's 1, we're going to AND port D with this number. Okay, so what's going on with this? So these numbers here are what are called masks. Okay, and so notice in this case, this number is all zeros and a 1, and it's a 1 in the particular place. What is this place? Well, this is pin 0, pin 1, pin 2, pin 3. So remember, port 2 is the input, pin 3 is the output. Okay, so we're setting port D pin 3 here when we do this. Okay, and so we're ORing whatever is in port D with this number. So what is that doing? Well, when you OR a pin with 0, it basically leaves the pin unchanged. Okay, when you OR with 0, it leaves the pin unchanged. If the pin was a 0, it stays a 0. If a pin was a 1, it stays a 1. Okay, so all of these bits, and so 0B means this is a binary number, and so I'm leaving all of these bits the same except for this one. And if I OR with a 1, it sets that bit. So this is one way of setting a bit in port D. Okay, and which bit? It's bit 3. Okay, so if the input on pin 2 is 0, then we set the output, which is on pin 3, to 1. Okay, we set the output to 1. So, and it leaves the other bits alone. So it doesn't change what's going on with the other bits. It only works with that one specific bit. So that's the idea of a mask. The mask basically is intended to work only with the thing that you're concerned with. Okay, so in this case, I'm doing an AND equals. Okay, and notice that the mask that I'm working with here is all 1s and a 0. Okay, so if I AND anything with a 1, then it stays what it was. Okay, if I AND a 0 with a 1, it stays a 0. If I AND a 1 with a 1, it stays a 1. So this basically ANDing with a 1 with 1s leaves the things unchanged. The thing, if I AND with a 0, however, I'm clearing that bit. Okay, so what this command does is it clears the bit. So when pin 2 is equal to 1, pin 3 needs to be the OR of that, and so basically this is clearing pin 3. Okay, and so these two commands together basically set the output which is on pin 3 to be the OR of what's happening in pin 2. Okay, can you see how that's happening? So this concept of using a mask is effective. And notice, so this command, well, actually this command is like the digital write. So the digital write, actually these two commands are like the digital write. And so it depends on whether you're digitally writing 1 or 0. And actually, the digital write does a lot more than just these commands, but it's actually doing these two commands. So in the digital write, when you send a bit or something to digital write to a certain pin, a high or a low, it looks at whether it's a high or low, and it will do one or the other of these two things. So it's actually doing this. The digital write is actually doing one of these two things. So, so this is what's happening with pin 2 as the input and pin 3 as the output. Here we have pin 0 as the input and pin 1 as the output. And we've actually, instead of specifying the bits out like this, I've actually written them in hexadecimal. Okay, so notice 2 is actually O2 is all zeros, and then this bit is 1. So that corresponds with pin 1. Okay, so that's just like this, except it's using a different bit. And this is just like that. Again, it's just using a different bit. Okay, so I can either specify them in terms of binary, or I can specify them in terms of hex. And so I can go through that, and I look at all the input pins, and I do that, and I work with the associate output pin. So in this case, for pin 4, its output pin is pin 5, and so here's the bit pin 5. In this case, pin 7 is connected with output pin 6, and so here's pin 6 being affected. Okay, and so this then does exactly what we were asked to do in that program. So that's what we have in this particular programming example. So you can see exactly what's happening in this. I check a pin, and I do something with it. And this is what so the fact that I can actually check individual pins. So this is like doing a digital read, and this is like doing a digital write. Okay, so when I do this, I'm actually doing a digital read, but I'm actually doing it much more efficiently than the Arduino command digital read does. Okay, so that's and it may be possible to make this even more efficient. I'm not sure how, but this works. This approach works. Okay, so there's our programming example. Okay, so here is actually what's happening when we go through and work with, here's the first one. Okay, so we have these various things that are happening when we do synchronization and when we read an externally applied pin value. I'm not going to talk too much about this. This actually, this notion is more critical, and we'll get back into this when we look more specifically at some of the timing issues when we're working with assembly language. So that'll be more important when we're there to look at that. And also synchronization so that was with writing, this is with reading, and so forth. So we'll look more at some of these things when we get to the assembly language portion, some of the timing. Associated with each port, we saw that we can use it as an input port, as an output port, digital in, digital out. But remember, there are alternate functions associated with every port. Okay, and so this is how the Arduino actually connects to those alternate functions. We have these quantities. Okay, so these signals, these are all signals, and you don't actually have access to these signals directly. These signals are used when you do other things, like when you set other pins and such. Okay, so so pull up, override, enable for pin and port X, pin in. Okay, so that's what these are. Pull up, override, value. So there's the enable, and then there's the value. Okay. Data direction, override, enable. Data direction, override, value. Port value, override, enable. Port value, override, value. Digital input enable, override, enable. Digital input enable, override, value. Sleep control, and port toggle, override, enable. So these are the various signals, and you can see how they arise in this logic. Okay, so you can see, for example, that what determines the pull-up, whether the pull-up resistor is connected or not, is the PUD, and also these values that come from somewhere. Okay, somewhere in the logic, and basically they're determined according to these names. Okay, so you have override enables, you have override values, and so forth. You also have these, again, pull up, disable, the write to DDR, the read from DDR. So these are with the DDR ports. These are the the read to a port, the write to a port. Okay, and this is a read from certain pin. So this is the read to the entire register. This is a read for a specific pin, and this is a write to a specific pin. So though you have options of writing to an entire port, or you have options of writing to specific pins or reading from specific pins. There's an I/O clock. There's a digital input pin on port X, and then there's an analog input-output pin on port X. So these are these are things that affect what's going on in here. So there's actually a lot of stuff going on. Okay, so what are some of these alternate functions that we're talking about here? What are the different applications each pins? We've kind of seen in our little block diagram the layout for these alternate functions, but let's see what they're actually doing. So we'll start with pin B for port B first. So here are the different pins for port B. So for port B, pin 7, we can connect to the crystal, the clock chip oscillator pin 2. So the clock chip oscillator has various pins, pin 2. There's a timer oscillator with pin 2. And there's also pin change interrupt number 7. So each of these port numbers have these different things going on with them. So I notice I can have things associated with timers, like the crystal oscillators, or these timers in terms of certain oscillator pins. I can also have pin change interrupt. So pretty much every port can have what's called a pin change interrupt. When we talk about interrupts in more detail, we'll explain what that's all about. There's also the SPI master clock on pin 5. There's the master in slave out for again SPI communication on pin 4. There's master out slave in for SPI communication on pin 3, and also there's this timer counter 2 output compare match A output. Wow, that's a lot of that's a mouthful. When we talk about the timers and counters, we can explain what that's all about. Slave select. Here's the slave select line for SPI communication, and there's also the timer counter 1. So this is timer counter 2, timer counter 1, output compare match B output. So each timer and counter has an output compare match A and an output compare match B. Okay, so notice here's timer counter 1, output compare match. So here's A, here's B, and this is A. Notice there's not a B here. That's because it appears on a different port. Okay, pin change interrupts. Here's a timer counter input capture input. Okay, and then here's the clock 0, the system clock divided, the divided output. So a number of outputs on port B, number of alternate functions. Here are what set those alternate functions. Okay, in particular for pins 7 through 4. Okay, so we have a number of things going on. So these are what determine what those alternate functions will be. Okay, so pin 7, if I want it to be crystal 2, that oscillator, timer oscillator, or pin change interrupt. Okay, so this is what determines what it will be. Okay, so you can see it's dependent upon a number of these functions, these signals, as to which of these will be. And so this is the overriding signals for those alternate functions. So there is a lot of signals and stuff going on if you want to use these alternate functions. But how else are you going to access that? You have one pin that can do all these things potentially. So you need to have some way of being able to switch between all those different functions. So this is what we have for pins 4 through 7, and then we have a similar set of things for pins 0 through 3. Okay, so first set, second set. Anyway, there's a lot of stuff going on here in terms of being able to specify these alternate functions. So that's what's going on for pin B. For pin C, we have these options. Pin C, bit 6 can be used as a reset pin or a pin change interrupt. Obviously, you need to make sure that you have them clearly defined, because you don't want to accidentally be resetting when you're trying to do a pin change interrupt. Analog to digital conversion input channel 5. So notice that these are all analog to digital conversion pins. Okay, so port C is associated with analog to digital conversion. And they can all be used as pin change interrupts. Here's the 2-wire system clock. Here's the 2-wire data. Okay, and so those are all the ports for the analog inputs can do. So these are primarily analog inputs, but they can again also be used. So notice that as analog inputs, the analog input is actually one of the alternate functions for these guys. So it's not really an alternate function. That's actually the primary function of these guys is the analog input. But they can also be used as pin change interrupts or whatever. For port D, we have these options. We have the analog comparator negative input port. So that's pin 7. Pin 6 is the analog comparator positive input. Okay. Again, pin change interrupts throughout. Here's the timer counter 0 output compare match A. Timer counter 0 output compare match B output. Okay. Here's the timer 1 external counter input. Here's the USART external clock input and output. Here's the timer 0 external counter output. Interrupt 1. So this is the actual hardware interrupt for that's wired in, as opposed to a pin change interrupt. Timer counter 2 output compare match B. So we saw that output timer counter 2 output compare match A. We saw that in port B, and here's the other side of that. Here's int 0. Here's int 1 external interrupt 1. Here's in pin 2 we have external interrupt 0, and then we have the transmit and receive for the USART. Okay, so these are all the alternate functions that we have, and now we've seen all the possibilities that we have for these various pins. Okay, so a lot of stuff going on, and they've obviously put a lot of work into getting these things to work with all of these possible functions. So for the most part, if you don't choose to use an alternate function, it just doesn't use the alternate function. Okay, it uses the primary function. So GPIO as output. So when you set a pin as an output pin, the pin is in a state of low impedance, so it has low output impedance. And as a result, the pin can supply current to other circuits, 40 milliamps max. Shorts or attempting to draw more current can fry the Arduino. Not a good, don't want to fry that baby. And then we can use external resistors to limit the current from the pins. So external resistors can limit the current from the pins. When it's an output, when it's defined as an output, it is low impedance, and you can't put in a pull-up resistor in that case. Okay, because it's defined to be a state of low impedance. The only time you can throw in the input resistor, input pull-up, is when it's an input. Pin 13 has an LED and pull-up resistor connected, so that is a special case. All right, as inputs, all of the digital and analogs can be used as digital inputs. When pins are set up to be inputs, they're in the high impedance state generally. Okay, and in this state they draw very little current, and as a result they don't load whatever circuit they're attached to. So when we talked about circuits, we talked about loading, and so since this has such a high input impedance, it acts like an open circuit, and it doesn't really draw much current. So if the pin is not connected to a circuit when it's in this high impedance state, it is called floating. And if you try to read the value, you'll get unpredictable values. The values could be all kinds of things. If you have a pin that's floating and it's next to a pin that's doing something, sometimes there's a capacitive coupling between the two pins, and this pin will start reading whatever's going on in this pin, even though you're not actually doing anything to this pin. So you can get some EMI, electromagnetic interference, going on. And that's especially likely when you have your input in a high impedance state when it's not connected to anything. So when it's set into a high impedance state and it's not connected to anything, that's when you're going to have some of this trouble. So in general, unconnected inputs consume more power than inputs that are either pulled high or pulled low. So if power consumption is important to you, then this is something you want to consider. Okay, that you want to throw in a pull-up resistor or a pull-down resistor in working with circuits like this. Okay, so it's important to keep that kind of thing in mind. Now, the last thing I want to talk about in this lecture today is the MCU control register. So that's MCU CR, microcontroller unit control register. And we have these different bits associated with it. The one we've kind of been looking at to this point is the PUD, okay, the pull-up disable. Okay, when this bit is written to 1, the pull-ups in the I/O ports are disabled, even if you've set them otherwise. Okay, so that's what the PUD does. Okay, so we saw that if you set a pin to be an input pin and then you write a 1 to it, that sets the pull-up resistor in general. If now you set this PUD bit, then that disables the pull-up resistor. So you can have it that way. And we saw those two different states and how the PUD came into play. And so that PUD bit is a part of the MCU CR register. Again, notice this is reddish here. That means these names are defined in the Arduino IDE, as is this name. So I can set that bit or not in order to work with this. Okay, so these other things are other things we'll get to later. So BOD stands for brownout detector. The I's here refer to interrupts, and we'll talk about those when we get to interrupts. But the PUD we saw it appeared earlier, and this is actually a bit that you can set. Many of those other signals that we saw we cannot set directly. They're part of the internal logic, and we can't set them directly. But the PUD is one bit that we can actually set directly. So, and this tells us what's going on with that bit. So this is all that you wanted to know about the GPIO, and probably more than you wanted to know. But anyway, here it is. We've covered this at a fairly deep level. Obviously, there's more that we could have gone into with all of those signals. I'm not going to go there, but we've seen the full scope of what happens with this GPIO, and we've seen actually even how to program more simply with using these registers. So the registers give us a very slick and efficient way of programming the GPIO. Thanks for watching.